Okay, my last video cut off on me when we were finishing this up. So we had this equal to pi, and then sine of 14 pi. So if we look at our unit circle, sine is going to be our y values. So sine of 14 pi is going to be 0. 0 is 0, and sine of 0 is also 0. So we'll end up with our final answer of pi. Alright, moving on to example number 4. We need to find the area of the region bounded by the graphs of the equations y equals sine x and y equals sine cubed x from x equals 0 to x equals pi over 2. So I went ahead and graphed this on Desmos so that we can see what it looks like. So this is kind of a cool graph. The red is sine x and the blue is sine x cubed. So when you put them into Desmos, you have to put the cubed on the outside. You can't put the cubed on the inside of the sine. So we want to find the area between the two curves between 0 and pi over 2. So in that whole region of our domain, sine of x is greater than sine cubed of x. So we'll do sine x minus sine cubed of x. Oops. Okay, so let's go ahead and set up our integral. We're going to say this is the integral of sine x minus sine cubed x. Alright, and from 0 to pi over 2. Okay, so I am thinking, let's go ahead and pull out a sine x, factor out a sine x, and see what that does for us. Because I'm kind of looking for that du, something that would make a good du. So if we factored out a sine x, we'd have 1 minus cosine squared x. Oops. Cosine squared x, that doesn't look good at all. Minus cosine squared of x. And then we would still, oh, no, I'm jumping the gun here a little bit. Aha. Okay, it would be 1 minus sine squared x times sine x dx. Okay, now this looks like it would make a really good du. So that means we would want a cosine in here. Well, 1 minus sine squared x is the same thing as cosine squared x. So let's rewrite that. We would have 0 to pi over 2 of cosine squared x sine of x dx. And then we could say that u is equal to cosine x, and du would then be equal to negative sine x dx. Okay, so now rewrite again. So we've got 0 to pi over 2 of u squared and du, and then don't forget the negative out there. Okay, and there we go. So let's go ahead and integrate that. We would have negative 1/3 u cubed. Yep. And then plug back in our u, so negative 1/3. And also, like we were before, we were talking about, like, we would change our integration limits of integration to be in terms of u. You can do that too. So that's up to you, however you want to do that. I'm just going to substitute this one back in, but either way. And that is cubed. Okay, so we've got negative 1/3 cosine cubed of x from 0 to pi over 2. And so that equals negative 1/3 cosine cubed of pi over 2 minus negative 1/3 cosine cubed of 0. And cosine is our x values. So at pi over 2, we're going to have 0. And then at cosine of 0 will be 1. So that gives us minus negative 1/3, which equals positive 1/3. And that's our answer for example number 4. Okay, so we have example number 5 is a particle moves in a straight line with velocity function v of t equals sine wt cosine to the 4th wt. Now w is a constant, so we're going to treat w like a constant. Okay, and we are not going to find what w equals. It's going to be in terms of w. Find its position function, x equals f of t. So x equals f of t, and that's our position function. So remember, we would start with a direction or a distance equation. So distance equation, and then we would take the derivative of that. Once we took the derivative of that, then we got the velocity. And then if we took a derivative again, we would get acceleration. So this was the order that we worked on distance and velocity and acceleration, how they're all related. So if we're given a velocity function and we want to know what its position function is, then we need to integrate our velocity to find what our distance is. In this case, they're calling our position function f of x. They're also telling us that f of 0 equals 0. That's just going to help us find c in the end. Okay, so we are going to take the integral of v of t dt, which is the integral of sine of wt cosine to the 4th of wt dt. And I'm going to rewrite that so it's a little easier to see what we want for our du. So I'm going to rewrite, so we've got cosine 4 of wt sine of wt dt. So I want this sine of wt dt to be my du, and therefore I'm going to say that u equals cosine of wt. Okay, so let's write that out a little better. So up here we will have u is equal to cosine of wt, and then du is equal to negative w sine of wt dt. Well, we only have sine of wt dt. We don't have a negative w, so we're going to have to divide both sides by that negative w. So when we plug that du back in, we're going to need that to be negative 1 over w du equals all of this. Okay, so now let's rewrite again. So cosine to the 4th of wt is just going to be equal to u to the 4th power. So we're going to integrate that. That w is a constant, so we can pull that out in front. So we're going to have negative 1 over w u to the 4th, and then du. So now we can go ahead and find the integral. And then substitute back in for w, or for u. So we get negative 1 over 5w lost where I was here. Okay, and then u is cosine of wt. And then we need to add in the plus c. I forgot that here. So add in what our plus c is. Now they've told us, now this is our f of t equation. They also told us that f of 0 equals 0. We're going to use that to find c. So negative 1 over 5w cosine w times 0 plus c is equal to 0. So cosine of 0 is equal to 1. So that's all going to go to 1. So now we have negative 1 over 5w plus c, which equals 0. and that will make c equal to 1 over 5w. So our final answer will be negative 1 over 5w cosine wt plus 1 over 5w. Oh, I forgot the fifth. Good thing I looked at that answer. Clear back here when I plugged my u back in. That should have been to the fifth. Sorry about that. That one there and here. Well, here too, but that didn't matter. Okay, so that's your final answer for example 5. Okay, for this example, I'm not going to go through and work the whole equation because they're all very, very similar, and I really want you guys to have some problems that are a challenge for you that you really have to think about. Obviously, you could just go through and put this into your calculator, but I am really going to be looking very hard at your work this time. So make sure that you know how to do this problem for the quiz and for the test. So on this one, we have, let's see, the natural log, whoops. Oh, and we want to find the length. So let's go back to that first. We want to find the length. So remember your length equation, the distance of a line, is equal to the integral from a to b of square root of 1 plus f prime of x squared dx. So this problem actually works out really cool. But use all of your purple sheet, your blue sheet, figure out what everything is. The f of x in this case is equal to the natural log of the cosecant of x. And so you're going to have to first of all find the derivative of that, which is going to be the derivative of the inside over the inside. So the derivative of cosecant x over cosecant x, which look up what that derivative is. And then you'll be able to simplify that. And then it'll simplify down really nicely. And then you just plug that in here. Oh, where'd my square go? And then you square it. And then you have actually end up with 1 plus cotangent squared, which that is part of our Pythagorean identities. So go to your Pythagorean identities and look up what 1 plus cotangent squared equals. And then you'll have the square root of something squared. So your square root will cancel out. And then look up what the integral of what's left over is. And then plug in your pi over 4 to pi over 2 and evaluate it from there. So it's actually a really cool problem. And if you can just put in what the exact value is, that would be great, and not just your decimal. Look for an exact value on this one. Okay, and that is all for this section.